Good morning, everybody. We are now at 8:05 on the school clock, and that's where I'm going to start every day. First of all, thank you so much for being patient yesterday. The tech people came in and gave me a new Chromebook during, unfortunately, third hour, because I teach pre-calculus first and second hour. They said they believe what was wrong was that all the settings for turning things off were still on the Chromebook. So I could only have the microphone for 20 minutes, I could only have the camera for 20 minutes, I could only have Google Meet for 20 minutes, and then it was going to shut off. So after that, everything worked great. So hopefully as we go through this today, you'll see a big improvement. All right. Again, if at any point while we're doing this you need to ask a question, don't be afraid to just holler out, Mrs. Cedarholm, this is so-and-so, and let me know what you need. We're going to start with zooming to uncover hidden behavior today. And again, you probably want that graphing calculator handy. And I do want to remind you that later on today we're going to be doing some regression. And when we do regression, we want to be able to see the correlation coefficient and the numbers that we need to tell whether or not we have a really good regression. So want to make sure your diagnostics are turned on. If you haven't had to, I guess if your battery didn't go totally dry, in my case, mine still have good old-fashioned batteries, and if I change those, then that setting goes away. So to turn your diagnostics on, remember you do second, 0, because that gets you to the catalog, and then we scroll down until we see diagnostics on. There it is. And then we have to hit enter twice, because the first time is just to choose it. And now it's on that main screen, that execution screen. And so then we hit enter again, and now it's done and it's turned on. We're not going to be doing linear regression today, but we're going to use some of the other regressions that we have in our stats portion of our calculator. So to start with, not with the stats, we're going to talk about zooming to uncover hidden behavior, and we've got find all the real zeros of f of x equals x to the fourth plus 0.1 x cubed minus 6.5 x squared plus 7.9 x minus 2.4, because we're continuing on our objective of figuring out how to graph polynomial functions, and that means all of them. So we want to make sure we can graph x to the first, x to the second, x to the third, any degree polynomial that we have, and talk about the end behaviors and the zeros and use that intermediate value theorem and model the polynomial functions. So with this one, before I start, and I heard yesterday that green is a bad color on here, that it's hard to see, so I'll go with blue. We need to know that the degree of this polynomial is a 4, and there are going to be 4 zeros. Now, there might be some imaginary, but there should be 4 zeros total. We're not guaranteed that they're all going to be real. And if we want to find these, the first thing we would do is say, can we factor this? And we look at it and we see that it has 5 terms. There's no greatest common monomial factor. So that's not something that we have learned how to factor yet. And that means we're going to have to go to the graphing calculator. And again, to save a little time today, I did already do some punching in. So you can either follow along with me and punch it in as you go. It's always best for you to give these a try as we're going through them so that you're sure that none of your settings are off. Sometimes your stat plots will be turned on and you won't be able to see these graphs. It's all of those little things that we don't want happening on test day. So there it is, x to the fourth plus 0.1 x cubed minus 6.5 x squared plus 7.9 x minus 2.4. And I want to graph it, so I'm going to try Zoom 6. And I see there are significant features of this graph that I am not getting on my negative 10 to 10 because this graph obviously has a local minimum down there that I can't see. So I realize that that has to do with my y's, and I need to change those. And I go into my window, and I'm just going to go big and say negative 50 to 50. Because I want to see this thing. And there it is. Now that means when I make my graph, when I transfer it to my test paper or my homework, that I have to realize I need to label that I'm going by 5s. Now, let's see if we could get away with a little bit smaller. Maybe just going by 3s, negative 30 to 30. And that fits a little bit better. Now, the reason we say this fits better is because it takes up more of the screen that we have here. And in that case, we'll see it a little bit larger and see a little bit more detail. So, before I get rocking on finding those, I want to make sure that I've labeled, and these are so tiny, I can't really label each one for you here, but 3, 6, 9, I'll go by 3s, 12, 15, 18, and that should be enough for anybody that's looking at my paper to know that I'm going by 3s. Now my X's, those were totally fine, but because I changed my intervals for my y-axis, I should really label my x-axis so people know, hey, this one is still going to be fine. So 1, 2, 3, 4, 5, 1, 2, 3, 4, negative 5. Again, tell somebody that's grading it, this is exactly what I saw here. Now, back to the calculator. And I have to figure out where those zeros are, so that's going to be second trace, number 2, and we'll pull up Blinky. And I usually just find these from left to right. Now, that's going to mean for this one, we remember that Blinky doesn't know above and below, he just knows left and right. That above it will be to the left, and below it will be to the right. So Blinky needs to be somewhere up there by my L, and press enter. And then I'm going to use my right arrow to move Blinky down below it to the right. And this is the first one I would write down. And I want to remember, we talked about this after one of the tests here, that this 1e to the negative 12th is the graphing calculator saying, I couldn't get you perfectly 0, but what I did get you was 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1. To us, that's 0, because we round to 3 decimal places. So we'll write this down as negative 3 point, oh, we're going to have to go with negative 3.100. We have to do some rounding there as well, and 0. Now to the next one. Well, the next ones, as I'm looking at this portion of the graph, it's kind of hard to see whether or not that really does cross or it doesn't. And so what I want to do is get a picture, a better picture of what's happening. And that's a really good job for Zoom Box. So Zoom, number 1. And Blinky was still over here, so we're going to have to move Blinky quite a bit. But what we're doing is we're moving Blinky to the upper left-hand corner of a box that we're going to make. So I think I'll put Blinky right there. And then I press enter. And then I use my down and right arrows to focus in on this portion of the graph where things were not super clear with the window that I had. And then I'll press enter again. And now when the graph comes back up, I have a much better look at the behavior that was happening, which they call hidden behavior on the graphing calculator. And now it's going to be a lot clearer for me to tell Blinky, hey, this is the left of the intersection and this is the right this time, so that I can find those zeros. We might miss that otherwise. So second trace, number 2. I'll get Blinky in position. Somewhere below it is to the left, enter. Somewhere to the right is above it, enter. And that one comes out to 0.50. Now we could write it as 0.50, but we should recognize that as 1/2 0. And we also should recognize that fractions are more perfect than decimals. So with this one, we'd want to write it down as 1/2 0. Now I'm back to find the other 2. And now the left and the right are going to be switching positions for the next 0 over to the right as we read the graph. So second trace, number 2. Blinky needs to be somewhere above the intersection with the x-axis and hit enter. And then right arrow somewhere underneath it, which will be to the right, enter, and enter through guess. And that one would be 1.133, 0. And we'll write all these down after I get them all found here. Second trace, number 2. And now we're below it to be to the left. Notice how that switches positions as we're reading these off. Enter, and then above it to be to the right. Now sometimes students will ask, how far above it, how far below. Try to get as close as you can because the calculator is actually doing calculus, and if we give it more area to cover, it takes it a little bit longer. It'll still find it, but it's faster if you keep it close. So that one would be 1.3670. So let's go ahead and get that on here. So from left to right, we had one that would have rounded to negative 3.1000. Then we had 1/2 0. The next one over was 1.1330. And then 1.3670. So we'll put those on the graph and see what we have. Negative 3 and a little bit more. 1/2 0. 1 and just a teeny bit more. And right next to it is the other one. Now, the parts that I know, I want to make sure I put in here. So I go back to the fact that this is the leading coefficient here of 1 and a degree 4 polynomial. And I realize that that's going to go up and up. So I can go ahead and put those 2 arrows on there. If this is on the test, I have to make sure that I have an accurate graph of what's happened. We wouldn't give you a graph unless we wanted you to do that. And since it didn't say sketch, we'd want to find those. Now, because we spent yesterday doing a lot of that, I cheated and wrote these down earlier so we can just know where those local mins and local maxes will be at. So we have a local min of negative 29.137 at x at negative 2.086. So remember we went by 3's, so that's going to be very, very close to the bottom of our graph. And then I found the local max, and that is just barely over the top of the x-axis, so 0.227, and that's at an x of 0.75. So then it comes back down to our next 0, and that one was a local min of negative 0.45. So again, barely underneath the axis, and that's why we had that hidden behavior when we first looked at this. We moved that up in case you want to write those in on there. But again, if this is on a test, just because it's asking for zeros, that doesn't mean we slop the rest of it on there. At the pre-calculus level, we're expected to do details. We have to have all of those little pieces put together. So, without knowing, I'm going to tell you that if you're not done with this, remember that I saved these notes and you could get this off. Hopefully, I didn't write so fast and go over everything here that you feel like you're way behind. All right. Now, different parts of our objective. We want to know polynomials inside and out. Our objective involved knowing everything about these polynomials by graphing polynomial functions. But what if we want to construct them? I mean, that's a big part of what people that are programming software need to do. They need to be able to visualize what's going on so that they can say, all right, if I just use a cubic here, if I just use a quartic here, I can give a visual of what it is we're trying to do to our customers. And this one says we want to find a polynomial with zeros of 2, negative 3, and negative 4. And that takes some backwards thinking because we have to realize that those came from, I believe your book uses a, an x minus a factor. So they want a polynomial. Doesn't say it has to be a function, but I'm going to go ahead and make it a polynomial function here. You could just use y, unless it says polynomial function. We want zeros of 2. Well, that had to come from x minus 2 as a factor, because again, those were the zeros, and 2 minus 2 would give you 0. And then it had to be x plus 3 in order to give me the negative 3. And then it had to be x plus 4 to give me the negative 4. Now, notice there's a lot of space here. So we are not done. We want to find a polynomial, and most of the time the instructions we give you on the test will be find a polynomial in standard form, because we want you to start with this, but then we want you to go ahead and multiply this out and see what that polynomial would look like. So it's a good idea to find the two easiest sets of parentheses and multiply those first. But in these, I really don't see anything easiest except that these two in the back both have a plus, so we're less likely to make a negative mistake if we do those first. So we'll do FOIL on those two and leave the x minus 2 alone for a second. So x times x is x squared, and then outside times outside is 4x, inside times inside is 3x, and that adds to 7x. And then last times last, 3 times 4 will give us the 12. And now we have to use distribution. So we're going to have to take this first x times everything in the second set of parentheses, write it down, and then take the negative 2 times everything in the second set of parentheses, write it down, and then we'll be able to move on from there. So we distribute the x, and we get x cubed plus 7x squared plus 12x. Then we distribute the negative 2, and we've got negative 2x squared minus 14x minus 24. Last but not least, we clean it up, and that's going to be by combining any like terms. We only have one cube. We've got 7x squared minus 2x squared for 5x squared. 12x minus 14x is minus 2x, and minus 24. And this we actually could check by putting it into the graphing calculator and making sure that it crosses at 2, negative 3, and negative 4, because that's what we wanted it to do. So if you want something to show up on a computer screen or a graphing calculator screen, this is how you do it. You build the polynomial to meet what you want it to do. If something like this also said that we needed it to be a quartic, well, then we could just multiply the whole thing by x, because then we'd have an x to the 4th in here. So there's different things that we can do to make what we need to appear. This next one says, let's find a polynomial with the zeros of, and we notice these are getting to be a little bit tougher. We've got 2, and then 1 minus the square root of 3, and 1 plus the square root of 3, which seems a little awkward, so let's write it up. I'm going to call this one g of x, realizing that comes from that same little x minus a factor. And here's where we want to remember, it's x minus the entire 0. We need to subtract that entire thing. And I hope your first impulse is, oh gosh, that means I should distribute a negative or something might go wrong, because that is an absolutely great impulse. Listen to that impulse. Now, this one would be a real bear to multiply it out. I mean, look, we've got a trinomial times a trinomial. Unless we can find a special pattern here that might make this go a little bit faster and a little bit easier. And one of the special patterns that we know about is a sum and difference pattern. And what's great about a sum and difference pattern is when you multiply them together, the outside times the outside plus the inside times inside cancel each other out. So I'm going to take a new look at those last two factors that I have, as this would be a plus and this would be a minus. Notice that x minus 1 is the same in both of these, and then in the back we have plus the square root of 3 and minus the square root of 3. So that's the sum and difference pattern, and that'll make this easier to multiply out. So I'm going to go ahead and leave that x minus 2 alone for a second. but I'm going to multiply these back to as sum and difference. So x minus 1 times x minus 1, that's going to give me the quantity x minus 1 squared. And then last times last, because I don't have to do outside times outside plus inside times inside. That's the beauty of sum and difference pattern. So this will be minus the square root of 9, which is 3. Now, I have to expand out that x minus 1 squared. So if you have to, you write it out twice. But we need that expanded, so you can do FOIL on that. A lot of times by this stage in the year, people are kind of able to do that FOIL in their head. And then before I distribute my x minus 2, I would want to combine like terms. Make it possible to take at least one step away. And that means I'm going to take my little x minus 2 times the quantity x squared minus 2x minus 2. So now I need to distribute my x. And then I need to distribute the negative 2. And finally, if we have any like terms, we need to combine those. And there we have it. So this is going to be g of x equals x cubed minus 4x squared plus 2x plus 4. And this one especially, you want to think about the fact that this did not have beautiful zeros. Here we had the 1 plus the square root of 3 and 1 minus the square root of 3. But we're still able to write a polynomial that will have those zeros. So this isn't a, I guess most people would say it's kind of a strange spot because we're really talking about graphing polynomials, but it's not, because we're saying, now let's work this backwards. Here are your zeros, now figure out what the polynomial would be. Let's know these inside and out and be able to go in both directions. People usually like those. They usually feel just like algebra again, so people like going through those. We're going to talk about modeling, and this was the part of the objective that we didn't get through in the last 2 days, and it just said model polynomial functions. And we've got designing a box, which we've done before. It says Dixie Packaging Company has contracted to make boxes with a volume of approximately 484 cubic inches. Squares are to be cut from the corners of a 20-inch by 25-inch piece of cardboard. I'm going to stop there and draw a picture. So we've got our little 25-inch by 20-inch piece of cardboard. And we're going to cut some length off of each of those sides so it can fold up and make an open top box, because that's what it said, the flaps folded up to make an open box. Now this C figure 2.31, actually if you go halfway down to the page, you're going to see a drawing that's very similar to the one that I just put up here. And it says, what size squares should be cut from the cardboard? Well, we're worried about volume. And they want that volume to be using the 20 and 25-inch piece, but we remember we're going to have to cut an X off of each end of that. So it's going to be 25 minus 2X and 20 minus 2X. And when we fold it up, X actually becomes the height. And then, yes, we want to expand this out. We want to see what it looks like. So we would go ahead and use FOIL on what we see for the 25 minus 2x and the 20 minus 2x. So 25 times 2500, and then outside times outside would be minus 50. Inside times inside would be minus 40, so minus 90x plus 4x squared. And then I'm going to go ahead and distribute the x, but while I do that, I'm also going to put these in standard form. So I'm going to have the highest power first. So x times 4x squared would be 4x cubed. X times minus 90x will be minus 90x squared. And then x times 500 would be plus 500x. So here's our model, minus one piece. And that last piece is, they did tell us they want that volume to be approximately 484. So we have this, and we have a choice here about how we can actually find the solution. In the past, we've said, hey, let's just make one of these sides y sub 1 and another side y sub 2 and find those two pieces. We've also said, let's go ahead and move the 484 over. Let's check and see if it's going to be factorable. And if it isn't, then we can put it in the graphic calculator and we can figure out where the zeros are. So let's go ahead and move everything over, because remember, the choice is always the algebra. And with this one, we have 4 terms. So our only hope of factoring this would be that we can go ahead and use factoring by grouping. So you look at 4x cubed minus 90x squared, and you think, well, I can pull an x squared out. I could pull a 2 out, but is that going to match what I would get if I were to try to factor 500 minus 484? And the answer is no. This is not going to be factorable by grouping. So that means what we need to do is we need to see this on the graphing calculator and then figure out where the answer is. And part of that is going to be thinking about, what should I have for x's and what should I have for y's? And we did discover before that that comes from a more in-depth thinking of what's going on with those factors. So we want to make sure that all of those factors are, well, 0 or higher. So 25 minus 2x needs to be greater than or equal to 0, and 20 minus 2x needs to be greater than or equal to 0, or we're not going to have a box. So we would go ahead and solve those and figure out, what should our highest domain x value be. We'd subtract 25 from both sides and divide by a negative 2, which of course means flipping the signs. So this one would be x needs to be less than or equal to 25 halves. We also know it has to be bigger than 0. And then the other one, we'd go ahead and subtract 20 from, and then divide, again switching the signs. And we find out, well, x being less than or equal to 25 halves, that wasn't small enough. It's going to be too big at 25 halves at 12.5. We've got to keep that under 10. So our x values, as we still think about it in terms of inequalities, our x values need to be between 0 and 10. But we would write that, of course, in our interval notation. So now, this needs to go in the graphing calculator so we can figure out what that x would be. I want to make sure everybody's time to write down any last pieces there. And I'm pretty sure that I put that one in the graphing calculator last night as well. So I will turn this one off and turn this one on. And there's our 4x cubed minus 90x squared plus 500x minus 484. But now I know a little bit more about the window. So my window for this one, I know I need to have it between 0 and 10. Otherwise, I'm not going to get a box. A little bit harder for people to think about is, well, what do I do for my y's? Well, we'll start at 0. But what you want to do is you want to think, okay, if I have to pick the highest number this could possibly be, then maybe I'll just think along the lines of a little number like 1 up here. If x came out to be 1, and I took 1 times 20 times 25, that would give me 500. We know it can't. That would be too much higher because it still wouldn't be 20 and it wouldn't be 25. But at least that gives us a number to try. 1 times 25 times 20 is going to give us 500. So let's put 500 in here. And it's probably more than we need, but it gives us a good starting place. Graph. Excellent. So we see there's actually 2 zeros there. Now, to let Blinky find those for us, I'm going to go ahead and put a few negatives in for Y. That way I can see above and below it. You might even want to go higher than that. Because what we have to do now is let Blinky tell us where those two solutions would be. And then it'll be up to the people that are ordering the box. So second trace, number 2. And again, I usually do these left to right. It's just a habit. That's how I read graphs. So that's how I find them. And there's the first one, 1.2220. And what we really care about is the box would be cut for that little x at 1.222. Second trace, number 2. Keep going, Blinky. You're almost there. But this time it's opposite because Blinky needs to be above it to be to the left and below it to be to the right. And that one is 6.8710. So those are the two solutions because we moved the 484 over into the polynomial. Let me just put it up a little bit so you can see the blue. We went ahead and worked it into a 0 on one side. And this is what we saw. And we knew that our two answers came from those two spots. So let's write those two down. We had 1.222 inches and 6.871 inches. Now, I wrote really big, or we would put this in a sentence, because obviously this is something a business would use, and so we could tell the customer that squares of side lengths 1.222 inches or 6.871 inches should be cut to maximize that volume at approximately 484 cubic inches. Now what the business is going to do is they're going to create one of each of those so that they can show the customer, here are your two choices, and you get to decide, which one do you want us to make. And that's an important part of this process, is making sure your customer can see all of those things. Now we have a second one here. I'm going to check the time real quick. Let's come back to this one. Since this is the same type of problem, I want to make sure we have time to get through the regression, and if we finish up with this, that'll be great. So what we're trying to do here is we're trying to find polynomials to represent situations. And that's a big part of learning higher math. You want to be capable of taking those higher paying jobs of programming. So just as any 2 points in the Cartesian plane with different x values and different y values determine a unique slant line. So 2 points determine a line. That's way back from the point line plane postulate in geometry. Any 3 non-collinear points with different x values determine a quadratic. Interesting. 2 points give you one line, power 1. 3 points give you a quadratic, degree 2 polynomial. In general, x plus 1 point's position with sufficient generality determine a polynomial function of degree n. The process of fitting a polynomial of degree n to n plus 1 points is called polynomial interpolation.
Miss Cedarholm,
yes.
It's happening again. The delay is happening again.
What's happening?
I'm still hearing you explain the previous problem, the one that is before the problem that you're on right now.
Did it just start?
So I don't really.
So, Etta, that's something you and I aren't going to have any control over because that has to do with server speed. So that's your server at home versus our server here at school. So
if you're saying something I can't hear you, guys.
You know what? I'll email you later. I'll email you later. We'll talk later. All right. So we want to do our interpolation here. And what they're saying is we can do perfect interpolation by finding how many points we have, subtracting 1, and making that the degree of the polynomial that we're using. So it says use cubic regression to fit a curve through the 4 points given in the table, which makes perfect sense. If we have 4 points and we subtract 1, we get 3, which is a cubic. So this takes us back to the reason that I had you turn your diagnostics on, which is we need to use the graphing calculator to find this cubic. So I'm going to turn this one off, and we'll go into stats and edit. And then you can see that I have the numbers from that first example of the interpolation there already in, and it's in list 1 and list 2. So now I'm going to let the calculator find that for me. Stats, calculate, and I want cubic regression number 6. And I do want it to use my first and second lists. I don't need it to store or anything like that. I just want to find it. And there it is. So now we can see the numbers that need to go in for A, B, C, and D. And here's what's fantastic. Look at this coefficient of determination number right there. Now, if we take the square root of both sides of that, that gives us an R value, a correlation coefficient of 1. That means this is perfect. And that's what they were talking about in that paragraph. They were trying to tell us 4 points, subtract 1, use a cubic. You've got yourself a perfect cubic regression model. So we'll go ahead and write that down to 3 decimal places. And for number 1, and it said fit a curve. It didn't say anything about functions, so again we could just go with y. 0.006 x cubed plus 0.018 x squared minus 0.501 x plus 0.977. And there is our cubic regression. And because r squared, the coefficient of determination, was 1, this is a perfect fit. And you know that's what we are after at this level of math, is always perfect, perfect. So now, when I went into Stats Edit earlier, you saw I already have the other numbers in here for the quartic regression as well. You might want to go ahead and punch those in quickly while I'm switching screens here. But this one has 1, 2, 3, 4, 5 points. 5 minus 1 is 4. A quartic should be a perfect fit. So again, Stats Edit, and these I have in list 3 and list 4, so I'll have to be a little careful as I go through that. So Stats, calculate, and this time I want quartic regression, and I have to change this to list 3 and list 4, and down to calculate. And there it is. Again, it's perfect. My r squared value is 1. So we'll go back here. And get that equation written down as y equals negative 0.375 x to the 4th plus 6.917 x cubed minus 44.125 x squared plus 116.583x. And then something a little interesting, that last number, our constant, came out perfectly as minus 111. And again, coefficient of determination was 1, so that means this is a perfect fit, which is always our goal. Now, down at the bottom, it says, always try to pick a model with the lowest possible degree. Absolutely, that's what we want to do. That has at least a reasonably good fit. So we want to watch that uppercase R squared, which is the coefficient of determination, but we also want to look for the correlation coefficient, if that shows up, and try to get something as close to 1 as we possibly can. All right, turns out, since I already had those punched in, we can go back and do that other volume problem as well. All right, so we're back to boxes. And this one says, obviously calculator permitted, an open top box is to be made by making this time a 20 by 40 centimeter piece of cardboard. And they're going to cut those squares just like we did before and fold up the sides. And A says, let's write an equation in the expanded form, so in standard form, of a polynomial function v of x representing the volume of the box in cubic centimeters in terms of x. All right, so back at it with our polynomials. They definitely wanted us to use v of x, and this one is going to have factors of 40 minus 2x and 20 minus 2x as we cut the x's out of both ends, and then again when we fold it up we'll have an x for the height. So we'll do the FOIL, and 40 times 20 is going to give us 800. Outside times outside minus 80x, inside times inside minus 40x, so minus 120x plus 4x squared. And then multiply again by the x and put it in standard form while we're at it. And then at this point we're wondering, well, what do they want? You know? We've got this open top box. We've written ourselves a model for it in terms of x. And then we go down to B, and they're kind of leading us through the steps that we used last time. And it says, what is the domain of v of x? For what values of x is v of x going to be greater than 0? So the relevant domain. The implied domain with this one, just like it was with the other one, would be negative infinity to infinity. But we know you can't have a box with negative sides. So we know that we have to go ahead and figure out, when is 40 minus 2x greater than or equal to 0? When is 20 minus 2x greater than or equal to 0? So that we can figure out what that upper value for our domain should be. So we'll subtract 40 from both sides and divide by negative 2, which flips the sign. And for this one we get x is less than or equal to 20. The other one, subtract 20 from both sides, divide by negative 2, and we'll get x is less than or equal to 10. So just like last time, we can't use exactly 10 because then we'd end up cutting down to 0 on the one side. But these are usually, we'll take them with square brackets or with the parentheses. And that's because of the way that the book defined it as using square brackets for the 0. So whether or not you put parentheses or square brackets here, it's going to be fine. All right, so there's our domain. And this would be our relevant domain. This is what makes sense for this problem. You know, common sense tells us that. And then for C, it says, what if we tell you that the volume of the box needs to be 1,500 cubic centimeters? Well, we put that in for v of x. And then we go ahead and subtract 1,500 from both sides so that we have a 0. And again, we'd want to try factoring by grouping, but obviously the numbers here are not going to work for that. And since the calculator is allowed, that's what we would want to use. So we would punch this in and see where those zeros are on this one. And I believe I already have this one in as well. I do. And I wanted to show you this one a little bit differently. So whether or not you set it equal to 0, or we say, here's y sub 1 and y sub 2 we'll be able to get this. And I do want to show you both methods, but if you said to yourself, I just want to learn the one way, I always want to have the 0 on one side, then all you would have to do is put the minus 1500 back here and find the zeros. All right, so I have those two in, and I go to my window, I still have the 0 to 10 in there. Maybe I'll get lucky and the negative 50 to 500 will still work with this one. I'll hit graph. Well, I can't see way up there where I need to see because I needed to see my 1500. So let me try 2500 to make sure I can see enough. And it appears, again, there are two spots where this will happen. But now this is using the intersection feature. So second trace, number 5. I'm going to move Blinky in position to find the left one first. And there it is. So the box would be cut at 3.486. And then the second one. Move Blinky over here by the second intersection. And that one ends up at a perfect 5. So the dimensions that would give us that 1500. We had, the first one was a decimal piece that was 3.486. And this was in centimeters. And the other one was a perfect 5 centimeters. But it did say give the exact dimensions. So what we would have to do is go back and put our 3.486 in each of these spots to find what the other dimensions would be. So 3.486 would give us 13.028. And 33.028 centimeters. And the 5 is a little bit easier when you put it back in there. That gives you 5 by 10 by 30. And then the last part of this said, well, let's go ahead and figure out what the maximum volume of the box would be. And for that, we'd go back into the calculator and we'd find this highest point, right? So the y equals, and here is the 4x cubed minus 120x squared plus 800x. And then, oh, I have to take that 1500 off. We're going to maximize this. So we don't want to know about that 1500. There we go. And let's try graph. I can't see the top of it, so I'll go back into my window and try that 2500 that I had in here earlier. Now I can see the top. Second trace, number 4, the maximum. So the left of the hill enter, the right of the hill enter through guess, and there it is. So to maximize the volume, we could get a little bit more than 1,500, 1,539.601 if we cut those at 4.226. So back here, the dimensions, we have x is 4.226 centimeters. And again, we'd have to put that back into our factors. So we could grab a calculator and take 20 minus 2 times 4.226 to get the other dimension, and then the third one would come from 40 minus 2 times 4.226. But to save time here, I'm just going to go ahead and give you those other two dimensions. 11.548 centimeters and 31.548 centimeters. and that would maximize the volume at 1,539.601 cubic centimeters. Phew. All right, so now that's everything. So we have finished up 2.3, and tomorrow will be the review on sections 2.1 and 2.3. Thanks for hanging in there. One person stayed the whole time.